Getting out through Christmas. So we only had gone friends. Figured we should drop in on Christmas. Well, maybe I was never diving on the New Year's Eve, but I know there and read this book damage. The thing about this West Coast, you know, Carl Benson. So, go pictures. They all do Faraday.
Yeah,
Yeah, he's near Exton. To Sheltered Bay, like a whole place. And it's not small, it's a huge area. But so when I dove there, snorkeled there. That's what we go into. Called Carl and Lana. I think you. And then we went back there. In it's very and it was like reminded me of like about that. That's like last time I was there, like, you know, never seen it like come around a few times. Like, wow, this has changed more than 50 conceived of, right? And like the coral formation will still intact church. No, I got the words that no lie. No, you were like, and I feel like outro. Yeah, perfect. Yeah.
All right, so I hope everyone had a good break. Oh, let me move this thing here. So we have, I think, oh, this is full screen. Okay. Why? Let's see if I can get rid of this stuff at the bottom. Wow. All right, good. So we have, I think, 3 weeks of class left. What we're going to do today is we're going to start chapter 7. We finished chapter 5 just before the break. And so I'm sure you've noticed that what we've done is we've skipped chapters 4 and 6. And so those are about electric and magnetic fields in matter or in materials. So my plan is to cover some of the essential material from chapter 7, and then we'll go back and we'll pick some topics from chapters 4 and 6, and we'll wrap up the course in that way. So today what I want to talk about is motional EMF and eventually get to Faraday's law, which in my opinion, there's almost nothing in physics that's had a bigger impact on society than Faraday's law. So Faraday's law is about changing magnetic flux, inducing electric fields, which can drive currents, and it is the heart of almost all of the power generation in the world. So whether you have hydro dams, nuclear power plants, burning coal, whatever you're doing, you're always using that heat that's generated or the water that's flowing in your hydro dam to spin a turbine. So if you're using nuclear power or burning coal, you're boiling water, which creates high pressure steam, and you're using that steam to spin a turbine. That turbine has coils of wire wrapped around it, and it's spinning through some fixed magnetic field. And so you get this constant changing magnetic flux through your coil, which induces the currents and the EMF, the voltage that is delivered to homes and cities and all that stuff. We'll also see why, if you're, you can sort of get an idea, why is power distributed in AC? Well, you've got these spinning turbines, and so the flux is increasing, then decreasing, increasing, and decreasing, and so you get this oscillating voltage and current. So let's get started. We'll start with the easy picture of this. So motional EMF, this arises when a wire is moved through a magnetic field. So initially, we'll be able to understand this effect in a pretty straightforward way, I think. So here's the picture. We're going to imagine we've got some region of space where there is to start with, a uniform magnetic field. And so inside this box, let's imagine we have a magnetic field pointing into the screen, and we'll just assume that it's uniform inside this box. Okay, so this is our magnetic field. Let me define a coordinate system. We'll say that this is our X direction and this is our Y direction. Okay, I'm going to make a little loop of wire, and that loop of wire will have some resistance. So I'm going to make this loop. And you could either think of the wire itself having some resistance, or we could imagine that we've got a fixed resistor at the end of our wire. So I'll draw in the fixed resistor. So there's R. Okay, we'll label some things. We'll say that this loop has a height H, like so. And what we're going to do is we need to move this through the magnetic field. And so what we're going to do is we're going to take this whole loop and we're going to pull it with velocity V to the right. So in our coordinate system, that's in the X hat direction. So what we've got is a loop of wire with resistor R is moved to the right with speed V. All right. Well, if you think about it, what we know is that inside our, say, copper wire, we have all these mobile electrons that can move around. Initially, if there's no voltage or no current in this wire, on average, all the electrons are just stationary. But then when we start pulling this thing to the right, now we have charge moving with some velocity perpendicular to a magnetic field. And we know that the Lorentz force law says that there's going to be a magnetic force on these charges. It's really electrons that are moving in the wire, but I'm going to draw it as if there were positive charges. It doesn't matter. It just makes it so that the positive charge flows in the same direction as the current that we're going to get. So we start with these positive charges. I'm going to focus in on the charges in this section of the wire. Maybe we can label from A to B. So if we just take one of these charges and think about what's happening, it's moving with velocity v to the right because we're pulling the whole loop. And if we do v cross b into the page, there's an upwards force on this charge and all of the other charges in this part of the wire. You could say the same thing for a charge over here in this horizontal section. You know, it's also moving with velocity v to the right, b cross b. There's a force upwards, but the wire is thin in that direction, and so it can't go anywhere. It doesn't move because of the magnetic force. But if I take these positive charges and move them upwards, then the electric fields that they produce are going to exert forces on its neighbors, and the whole circuit is going to flow with a uniform uniform current. And so there's really two effects. There's the magnetic force on the charges in this section of the wire, which start them flowing, and then their electric fields exert forces on all the other charges in the wire, and you get this uniform flow of charge. Okay, so whoops, sorry. The force, no. So the force on, I'm a lefty, I have to write on this thing upside down. Force on the mobile charges in the section that we've labeled AB of the wire is, I'm going to label this Fs. It's like our source force, and it's really a magnetic force in our case, and it is just Q, the charge. I'm going to assume that these are positive charges with the elementary charge E, and then it's V cross B. But the way we've contrived this example, V and B are perpendicular, so the cross product just results in a product of magnitudes, and the direction we said would have to be along the positive y direction, and so I'll call that y hat. Okay, and so this drives a clockwise current in our loop. All right, so fair enough. The equivalent circuit would be something like, we still have our resistor, and if it's an equivalent circuit, we would have current I being the same current I that we end up with in our loop of wire. But the only way we can drive a current in this equivalent circuit is by providing some voltage or an EMF. And so what we're going to be interested in is trying to figure out the value of this EMF or this voltage. So there are really two forces driving charge around the loop. One is this Fs, which is our source force. The source force could be a bunch of different things. It could be, you know, the most basic one would be just physically put a battery in there. It starts charge moving across the battery, and then the electric fields of the charges take over and flow charge all the way around. Or in our case, it's a magnetic force. So this is F magnetic in our example. Okay, and the other one is Q times the electric field. So this would be the electric interaction between adjacent charges. It's really just Coulomb's law. adjacent. No, that's not right. Adjacent charges. Okay, so then if we wanted to, we could write down kind of sort of a net force per unit charge. So net force per unit charge would be what? So F divided by, I don't know, E in our case, which I'm going to write as lowercase f is force per unit charge. Well, it's going to be the source plus the electric field. All right. But if you have a steady current, then the charges are moving around the loop at a constant speed, a constant average speed, let's say. And if they're not accelerating, then the net force must be zero. So for a steady current, charges move around the loop at a constant average speed such that this net force per unit charge is equal to zero, and that's going to imply that the electric field is equal to minus the source force per unit charge, which for us is a magnetic force. And that is this EVB divided by the charge E is VB in what we said was the y-hat direction. Okay, well, if I want to calculate EMF, I can calculate it from the electric field. So actually, this would be a negative sign in here, right? We calculate the magnetic force was EVB. We divide by E, we would get BB, but we want the negative of the magnetic force. Okay. Well, it's differences in voltage that create electric fields that drive the flow of charge, and we can calculate voltage differences or EMFs as minus the integral of E dot dl. And so we go from A to B of F magnetic dot dl, where minus E is equal to plus F magnetic. So that's just VB dot dl. And this turns out to be VB times H, because we're going to integrate from A to B, and from A to B is just the height of our loop. Okay, and so this is already the key result for motional EMF. And this is really the heart of kind of electric generators, moving wires, loops of wires around through magnetic fields and creating these EMFs that will drive currents. All right, so that's pretty interesting. If you think about it a little bit, we said that because magnetic forces are always perpendicular to the magnetic field, the magnetic force can't do any work. So how do we reconcile with, there's no batteries or anything, so what's doing the work in this problem? So recall that magnetic forces. Yeah, what I said was wrong. I said the magnetic force is perpendicular to the magnetic field. That part is true, but they do no work because the force is gonna be perpendicular to the displacement of those charges. Sorry, what am I at work is F dot DL. Yeah. Anyways, I'm a little bit confused at the moment, but it is true that magnetic forces do no work. And so the question is, what is the source of energy slash work that drives the current? Okay. So I want to draw sort of a little simplified picture of our setup. So we had a uniform magnetic field, and we had our loop of wire being pulled to the right. There was our resistor, R, and we're going to pull this with velocity V to the right. Okay, this was height H. Well, again, I want to focus on this region from A to B. The current is going all the way around this loop, of course, but if I have a current inside a magnetic field, I'm going to get a force on that current. Remember we talked about parallel currents, and we said that if they were parallel, they attracted one another. So the magnetic field due to the first current at the position of the second current exerts a force on that, and there was an attraction if they're parallel currents. All right, so the force on current I in section AB of our loop is force on this current was I cross B times the length of the current, or the wire. So let's see, we have a current going up, and we have a magnetic field into the screen. And so the force on that current is to the left. So this is in the direction of minus IBH, and it's in the X direction. So this is X, Y. So what that means is if we were to take this loop of wire and, like, imagine we just gave it a kick and it started going off to the right, then it would stop itself because the magnetic force on that current would accelerate it in the opposite direction, and it would eventually just come to rest. So that means if I want to sustain the current by having this loop move at a constant speed to the right, then I have to constantly balance this magnetic force on current I. So this would be the force Fi. And the only way I could balance that is by pulling it in the opposite direction with an equal magnitude force. And it's the work of F pull, that F pull times the displacement would tell me the amount of work I have to do. And that's the energy that's being put into the system to sustain that current. So in order to keep our loop moving to the left, to the right with constant speed, we need to offset or balance Fi with an F pull of equal magnitude in the opposite direction. So whoever or whatever is supplying F pull is doing the work to sustain the current. All right. Does anyone remember if you're applying a constant force on an object to move it at a constant velocity, how do you calculate the power? So work is force times displacement. So that's an energy. So how do you get a power from an energy? Yeah, divide by time. And so now you have displacement divided by time. And so what is that? Velocity. Yeah. So it's force times velocity. So the power supplied by pulling force is P pull is equal to F pull. In general, it's dot product with the velocity. In this case, it's a contrived example where these are in the same direction. And so this just ends up being F pull times V. But we calculated F pull. It was I times the magnetic field times the height of the loop. So I, B, H is the force, and then we multiply by V. Okay. Well, let's push ahead a little bit further. But the current, if you look at our equivalent circuit, is just going to be the EMF divided by the resistance. And we calculated the EMF, VBH. So the current is VBH divided by R, which is VBH divided by R. And we can substitute that in for here. And you can see what's going to happen. VBH times VBH. We're going to get that squared divided by R. And so therefore, power pull is going to be VBH squared divided by R. All right. It kind of has some nice features. As you might have guessed, that the faster you pull it, the more current you're going to get, and the more power that you're going to have to input to do that. The stronger the magnetic field is, the more current you're going to get, the more power you're going to have to supply. H, if that H was long, then you have a long piece of wire moving through this magnetic field. So you get a lot of magnetic forces on a lot of charges in that section of the wire. You get a larger current. You have to input more power. Okay, let's just do one little thing here. Note that the power dissipated by the resistor is, well, I squared R. But we just said I is the EMF over R squared multiplied by R. So that's going to be EMF squared divided by R. EMF is VBH. Got to square it. Divide by R. And the power supplied by the pulling force is exactly equal to the power that's dissipated by your resistor. So if the I said the resistor could be maybe just the resistance of the loop of wire itself. It could also be like some device that you're trying to power. And so you're pulling this loop of wire through this magnetic field to operate some device. That device dissipates all of the power that's provided by the force of you pulling on this loop. And so that's conservation of energy. The rate that you're supplying energy is equal to the rate that you're consuming it. So that's kind of interesting. There's a nicer way of obtaining the same sort of results. So what we're going to do is we're going to consider the magnetic flux by through the loop at some instant in time. Okay, so I'm going to draw the same picture again. So we have our magnetic field going into the screen. We're going to have our loop of wire. Here's resistor R, and this is moving at some velocity V. So we labeled some stuff already. This was height H. I'm going to add another dimension. I'm going to say the length of the loop that's actually inside the magnetic field is X. Okay, so how do you calculate magnetic flux? Flux is equal to what? In the simplest case possible, we have a pretty simple case here. No change. We're going to get to the change, but we're not there yet. I just want the pure magnetic flux. Yeah, field times area, that's right. So in general, it would be B dot dA around some closed kind of area. I guess I won't do that. Maybe that would imply a closed surface. But if our dA is perpendicular to the loop, then it's parallel to the magnetic field. So the dot product is going to be cosine of 0, which is 1. The magnetic field, we've chosen it to be uniform, so that comes outside. And for our simple case, this is just B times A. But the relevant area is just the part of the loop that's inside the magnetic field. And that has a base of X and a height of H. And so it's just H times X. And so this is BHX. Okay, and now we're getting to what you wanted to do. You wanted to take the time derivative of this. So consider d phi dt, which is going to be d by dt of BH times X. We said B is constant, so that's not changing. H is just the height of the loop. If we're not deforming the loop, we'll call that a constant. So the only thing that's happening is as we pull this thing to the right, X is shrinking. So we're getting less and less of our loop area inside, immersed in the magnetic field. And so X is the one that's changing. And so this is BH dx dt. But that's clearly just the speed that it's moving. It's not, I haven't done this exactly right. What did I get wrong? Yeah. X is shrinking with time, and so we get minus the speed. So what we could do is we could say this is minus the EMF that we calculated before. We calculated EH times V. And so therefore, at least in our case, we have found that the EMF is equal to minus the derivative of the flux with respect to time. So if this was a first year class, this is where we would stop and we would just say, well, it turns out that this is always true. And it is always true, but what we're going to do is we're going to try to work out a little bit of a more general proof that this applies not only to uniform magnetic fields with rectangular loops that are perpendicular to the field and so on. We're going to allow a loop of any shape in any kind of magnetic field, and we can distort the loop. We can have its velocity be weird, where part of the loop is deformed in one direction and part goes the other direction. And you can do whatever you want, and we want to show that we cover that same result. All right. So we now attempt to prove that this results that the EMF is minus the derivative of the flux, time derivative of the flux, is generally true for any shape of loop moving in an arbitrary way in a non-uniform magnetic field. All right, so let's see what we can do. So what I'm going to do is I'm going to draw some loop of wire, and this is at, say, some time t. It's inside a magnetic field, but I'm not going to draw the magnetic field. So there is a non-uniform magnetic field, which is just not showing. So the field lines could be going in any arbitrary direction. We could have a weak field here and a strong field here pointing in different directions. That's all fine. Okay. And then we're going to allow time to evolve a little bit. And our loop is changing its shape. And so it's a little tricky to draw, but I'm going to say, you know, maybe, well, that was a bit extreme. So let's say something like so. And so this is our loop at time t plus dt. And so if you'd like, we could think of this point on the loop ended up over here. And this point on the loop ended up over here. And you could keep doing this sort of thing to show kind of the evolution of our loop. So this is the loop at time t. This is the loop at time t plus dt. And what you end up with is sort of this ribbon of area that connects the two. And the change in flux from time t to t plus dt is whatever the flux is through this ribbon. It could be positive, it could be negative. It depends on the direction of the fields and how the area of the loop changed as it was distorted. So over here, we have, say, some current at time t, and then over here, we have a different current at time t plus dt. And Again, this current could be bigger or smaller than the original one. It depends on what was the rate of change of flux at this time compared to how it is at this time. All right, so let's see if we could work this out. The change in flux is going to be d phi, which is phi at t plus dt minus phi at time t. And that's just going to be whatever the flux through this ribbon is. And so this is a ribbon that's connecting the loop or loops at t and t plus dt. Okay, so now is the time where we do have to use the more general form for the magnetic flux, because we're allowing that, you know, these normal vectors for the areas could be changing direction all the time. B is changing its size and direction all the time. So it's a complicated situation. And what we have to do is we have to integrate over the area of this ribbon. Okay. So what we're going to do is I'm going to imagine taking one section of this loop at time t and at time t plus dt, and we'll zoom into that. Like we'll zoom into one of these little boxes that are connecting the points at different times. So let's zoom in. All right, so what we've got is, say, well, okay, we'll draw a section of this. And so there's these kind of things. And so this is point P, and this is point P prime at some later time. And so what that looks like is the area of that section is something like this. Now, if there was some current in this wire, we would say the step size from here to here, we'll call that dl. Okay, so we'll just say this is, vector dl. It's basically just determined by how finely we chopped up our ribbon into these little sections. And then the point P starts here at time t and ends up over here at t plus dt. Now, the loop was moving, like remember for our simple example, we were actually pulling the loop. And so there's something that's distorting this loop. And so each part of the loop is moving with some velocity. And to go from P to P prime, it must be whatever the velocity was times dt. So if we imagine that from time t to t plus dt is some short time interval, we could assume that the velocity was more or less constant during that dt time. So if I have these two vectors, how do I calculate the area of this thing? Not products. And yeah, multiply, it's a vector product, but which one is cross product, right? So this is supposed to be you know, these parallel sides. I probably didn't draw it great. So the area of this object is, well, dA is equal to the cross product between the two sides, like so. Now dt is a scalar, so I could pull that out of the cross product, and I could say this is v cross dl times dt. Okay. So what we set out to do was to calculate this d phi, which we said was just the flux through the ribbon, which was this integral over the ribbon of, let's see, b dot dA. But now we have an expression for this dA, and we're going to plug it in there. So it's the integral over the ribbon of, let's see, b dot, and then for dA, it's v cross dl dt. Now, what we're really trying to get at is an expression for the EMF, d phi by dt. So let's divide by the dt. So therefore, d phi dt is equal to the integral over the ribbon of b dot v cross dl. All right. So we're getting close. You could actually start to see the solution we want emerging, because the EMF, what was the expression for the EMF in our simple example? Yeah, VHV. B and V and this DL, you know, maybe something useful is going to come out of this. Okay, so recall, however, that we had this property for, you know, this is kind of like a double product, right? Of, or if you want a triple product, 3 vectors multiplied together. So we want B dot V cross DL. So remember, one thing I can do is I can permutate these vectors. As long as I keep their order the same, the result would be equivalent. So we need the order to be B, V, DL. So I could shift everything over. I could do a DL dot B cross V. All right. What does B cross V remind you of? Where do we see B cross V? Lorentz force. But in the Lorentz force, it's not B cross V. What is it? Yeah, it's Q times V cross V. So I want to switch this. What happens if I switch the order of vectors in a cross product? Pick up a negative sign, right? So I could write this as minus, I'm going to do it this way, V cross B. And then it doesn't matter if I do the dot product first or after, that doesn't matter. Okay. But so this V cross B is just the magnetic force. But recall that F magnetic is just equal to QV cross B. So therefore, V cross B is the force per unit charge, which we called little f. All right. So if we combine all that stuff, what we had was the derivative of the flux was equal to, well, it's now an integral over our ribbon. And our ribbon is like a closed surface, goes all the way around. Of, let's see, instead of B cross DL, we're going to write that as minus V cross B dot DL. So we pick up a minus sign. V cross B dot DL, which is equal to minus the integral of this F magnetic which was like our source force that starts the flow of current around our loop. And if we go back, I think we're going to find somewhere, I hope. Yeah, here it is. This F magnetic.dl is equal to the EMF. Actually, I don't know why I put a circle around. Let me just call it F ribbon. The integral around the ribbon is what the notation we were using. But this was just equal to minus the EMF from earlier. And so therefore, we get, well, maybe I should write it this way. The EMF is minus d phi dt, and we didn't assume anything about the fields being uniform, how the shape of the loop was, how it was distorted, and we recover the same results. Okay, so what I want to do is I want to do an example problem, and this will be like our AC generator. How do we generate AC power? So this is true for any loop moving in any way in any magnetic field. All right. How are we doing here? Oh, not bad. Okay. So the example that I want to do is problem 7.10 in Griffiths. So it's the AC generator. I think this is 7.10 in the 5th edition. It might be a different number if you're working from a different edition. But anyways, what we're going to have is a square loop of wire with resistance R, which spins with angular speed or angular frequency omega in a uniform magnetic field. And so what we're going to try to do is we're going to try to find the current I in the loop. Okay, so a picture is worth 1,000 words. So let's draw a picture of this situation. Here we're going to have our magnetic field, and I'll just draw a uniform magnetic field, say along the positive x direction. And then I'll have, this is like my rotation axis, and so we're going to have some rotation around this axis. Let me just remind you that omega, when you write omega as a vector, use the right-hand rule to find its direction. So if we're spinning around this axis, I curl my fingers around the axis, and then my thumb gives the direction of the angular velocity vector. So it's up in this case. All right, and so I'll draw my loop. It's supposed to be square, so I'll try to get that about right. And then we'll put some resistor R somewhere in our loop. And so here's our rotation axis. What we'll do is we'll make the loop size something like d by d. So it is square. All right. Well, all we're going to do is we're going to try to work out the time derivative of the flux. This is easiest to do if we imagine kind of looking down from above. So let's redraw this with a top view. Okay, so my field is still uniform and pointing to the right. But now I'll draw my loop and it's rotating in some direction. This time omega is pointing out of the screen. And this is still the distance d is the length, looking from the top. Okay, well, if we were to draw a normal vector to the loop, it would be something like n hat. And so we could write that A, our A vector, is going to have the area of the loop, which is p squared, and it points in the direction of the normal vector. Okay. We need that because if I want to calculate the flux for a uniform magnetic field, I don't need to integrate. I just need to evaluate the dot product between B and A. All right. If we use a standard coordinate system, we'll have x hat off to the right. So our magnetic field is in the x hat direction. And so what we get is B times d squared. And then B is in the x hat direction. And then we have a dot product with n hat, or the area vector. What is the dot product between these two? What is that going to give us? If you take the dot product of any two vectors, you get the product of the magnitudes in one. Yeah, cosine theta, where theta is the angle between the two vectors. B is horizontal, and n hat is off in some direction. So theta is this angle. Now, the magnitudes of these two unit vectors are both 1, and so this is just going to be cos theta. And so therefore, our magnetic flux is equal to B d squared cos theta. If we wanted to, right now, we could just take a time derivative. We would have to use chain rule. So the cosine would become a sine, and then we'd have a d theta dt. What's d theta dt? Yeah, it's just omega. So another way to do it is we could say, look, I know that n hat is constantly changing direction. And so therefore, what that means is theta is always changing. But if I'm spinning my loop at a constant rate, I could just say theta is equal to omega t, assuming that we choose theta to be 0 and t equals 0. And so in that case, my magnetic flux becomes the magnetic field strength times the area of the loop, cos of omega t. And so therefore, the EMF is equal to minus d by dt of the flux, which is minus d by dt of b d squared cos omega t. And so now, I mean, I guess we still are doing chain rule. The omega comes out, the cosine becomes a minus sign, which cancels the minus sign that's out front. And we get that the induced EMF is omega b d squared sine omega t. And this is clearly an AC EMF. And this is really the basic arrangement of all power generators that we're currently using. Of course, you know, if you have solar or something like that, that's different. But even wind, like wind is still spinning a turbine. The only difference is that instead of having a single loop, you'd have many, 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 many loops, and you would get this induced EMF in each one of those loops, and they would add in series. So if you had n total loops, you would just have a factor of n out front, and you could really amplify the voltage that you're generating in that way.
D squared because the length of our loop is D and D.
Yeah. Yeah, I didn't have to do that. It could be like X times Y or something like that. Yeah. Or I know for all you could make a circle. Yeah, for sure. So let's just do. Oh, right. We said we were going to calculate the current. So I is epsilon over R. And so I mean, that's not interesting. We're just dividing by R. Sine omega t. So this would be I naught. This would be minus I naught, where this coefficient is just I naught. And so this is an AC current generator. All right. So what I want to do is I want to generalize this EMF that's induced by magnetic flux and see where it leads, because I can change the magnetic flux through a loop in a bunch of different ways. Well, three different ways. Okay, so we're into 7.2 now, and we're gonna get into Faraday's law. And Faraday's law is about induced electric fields. Okay, so an induced EMF is observed whenever there is a change in flux. Change in, I guess I should be specific, magnetic flux. Okay, we've just used and we have proved that the time derivative of this flux with a minus sign gives the induced EMF. All right. There are three ways to change magnetic flux. All right. One thing I could do is I could change the area of my loop. And so the motional EMF that we did was an example. We weren't actually physically distorting the loop, but we were pulling it out of a region of constant magnetic field. So the amount of area of the loop that was inside the field was changing. You could also you could just have a uniform magnetic field throughout a huge region of space. You could take a circular loop of wire and just pull it so that it closes, so the area goes from pi r squared to 0 very quickly, and that's changing the area, and that would change the flux through the loop, and you would get an induced EMF while the loop was changing its shape. So one is we can change the area of the loop. And so effectively, motional EMF is an example Okay, two. Well, what else could we do? We could change the relative orientation of the magnetic field and the area of the loop. And our AC generator was an example of that. We had a constant magnetic field. Our loop size wasn't changing. It was always all inside the magnetic field. It's just that how much was the plane of the loop aligned with that magnetic field? So we could change the relative orientation of the loop and the magnetic field. And so this was like our AC generator is an example. In both of these cases, we could understand these effects using the Lorentz force. We had a stationary magnetic field and we were moving charges around throughout that magnetic field. The way we're removing the charges is we just had free electrons in the wire and we moved the wire around. That gave the electrons a velocity. The Lorentz force caused some motion and a flow of charge and current. So this can be understood from the Lorentz force. Okay. What's the third way I could change magnetic flux? Yeah, so I could just change the strength of the magnetic field, for example. One way to do that is I could have a fixed loop and I could take my bar magnet and I could pull it away, for example, to make it the magnetic field weaker and reduce the flux through the loop. Well, in that case, the wire was always stationary, and so the charges would not have a velocity. And so, you know, it's not necessarily so obvious that the Lorentz force is at work here. Although, if you say all that matters is the relative motion of the field and the charges, then you sort of recover that same effect. So we could change the strength of B. So, you know, pull a bar magnet away from a stationary loop, for example. Okay. So in 3, the charges in our loop of wire are stationary. And the magnetic field is changing. So what Faraday did is he deduced that what must be happening is when you're changing the magnetic field, it's inducing an electric field at the position of the loop. And that electric field is what's causing exerting the forces on the charges that get them to flow, to establish that current. So Faraday deduced that the changing magnetic field induces an electric field that can drive the flow of charge in the loop. In fact, even if you don't have a physical loop in place, you would still have the electric field would be induced in that region of space. So what Faraday said is that the induced EMF was equal to E dot dl around a closed loop, which was equal to minus d phi dt. And if you look at this, this is already a little strange. What's strange about this closed loop integral for the electric field? Yeah, how do we usually picture electric fields? If you wanted to create an electric field, what would you do? Get a charge, right? So you would have electric fields would be coming out of, say, pointing away from positive charges and then terminating on, say, negative charges. This implies that you have an electric field that's forming a closed loop. And so we haven't seen that before. So note that this is already unusual, as it implies an induced electric field that forms a closed loop. Okay, well, anyway, let's just keep going with this. So if that's true, I would have E dot dl is equal to minus d by dt of the magnetic flux, which is B dot dA, the integral of B dot dA. All right, so what we're going to do is we're going to consult our old buddy Stokes' law, and we're going to convert this line integral to an integral over a surface. So we'll invoke Stokes' law, which says that we would have the curl of E dot dA is equal to minus. Well, what I'm going to do is I'm going to take the time derivative inside here. In the current picture that we're working with, we're assuming that it's the magnetic field that's changing, right? We're going to imagine, say, some fixed area and some fixed orientation between the two. So the time derivative is going to be applied to the magnetic field. I'll write it as a partial derivative because this field might also depend on the position coordinates. And then we have dot dA. And so now the only way that these two things are equal to each other is if the integrands are equal. And so this requires that these things are equal. And so that is Faraday's law, which says that curl of E is equal to minus dB dt. And this is one of the ways in which you really see the close kind of interconnection between electric and magnetic fields. If I have a changing magnetic field, that necessarily creates an electric field. We'll see a little later that the opposite is also true. If you have a changing electric field, you'll create a magnetic field. And so that's why if you have like electromagnetic waves or something like light, it always comes in a pair of oscillating electric and magnetic fields that turn out to be perpendicular to one another. Okay, so first, the last thing we'll do. Oh, we've got a couple minutes left. Are we really gonna? No, we'll save that for later. So let's note that if B is constant, say magnetostatics, we recover the curl of E is equal to 0. In the last minute or so, let's go back and look at this. When you calculate voltage differences, what you usually see is that minus the integral of E dot dl is equal to a voltage difference. But we've dropped the minus sign here. So that's something that's worth looking at. Let's just quickly look at a battery. The simplest circuit you could imagine. So here's V, here's R, and we know we're going to get a current that moves around here. So the terminal of our battery, we have a positive one here and we have a negative one here. So if we have a current going around clockwise, what that suggests is that we have an electric field that is also going around clockwise. That's, for example, pushing positive charges around in that direction, or equivalently negative charges in the counterclockwise direction. And what we're used to thinking about is that electric fields point from high potential to low potential. So if we had something like, say, high potential here, which would correspond, how do you make high potential? Maybe I put a bunch of positive charge on an electrode. And then over here, I have a low potential, low voltage. And I do that by putting a bunch of negative charge on some other electrode. And then what I would expect to get is my electric field pointing from high potential to low potential. So E points from high to low potential. But if we look through the battery here, we seem to have the opposite case, right? We have an electric field going from the low potential side of the battery to the high potential side of the battery. So why is that? How is that possible? What's happening there? There's chemical energy in the battery. So it's the chemical energy that's taking the charges and moving them from low to high potential. So they're doing work to overcome that potential barrier. And so the same thing is happening when we think about induced EMFs or induced electric fields from changing magnetic flux. And so that's why that sign's not there, because the changing magnetic flux is doing the work to move the electric field, to generate that electric field and have that potential difference that drives that current. Okay, good. So I think that's where we'll stop. We'll start with an example next time. You may have seen it before, of like the jumping ring, where you have a solenoid and you suddenly change the current in that solenoid and have like that big ring fly off there. Okay, so we'll analyze that case next time as a starting point. All right, thanks everyone.